Number 4, warm up to FTC 1. You may use FTC Part 2. Part A says evaluate the integral, and it's the definite integral from 1 to pi of 6t squared minus 2t plus 3 dt. So using FTC 2, we get 2t cubed minus t squared plus 3t, evaluated at pi and at 1. So this is 2 pi cubed minus pi squared plus 3 pi, and then minus 2 minus 1 plus 3. So let's see, all of this is 4. So we've got 2 pi cubed minus pi squared plus 3 pi, and then minus 4. So that's part A. Part B says evaluate the integral from 1 to x of 6t squared minus 2t plus 3 dt. So almost the same thing, but now your upper limit of integration is an x. And what you do is pretty much the same thing you did in part A. So 2t cubed minus t squared plus 3t, evaluated at x and at 1. In other words, FTC Part 2 still applies, even if you don't know which x is being your upper limit of integration. And so FTC Part 2 still applies in this situation. Whatever x is, you can apply FTC Part 2 to this definite integral. And so when you do the actual plugging in part, you get 2x cubed minus x squared plus 3x, and then minus 2 minus 1 plus 3. So this works out to be 2x cubed minus x squared plus 3x minus 4. So if x is actually equal to pi, we get what we got in part A. But if x is like 1,000, this definite integral would work out to be whatever this final answer is, but with 1,000 plugged in for all the x's. And so what this is telling you is this definite integral here, this is a function. And you can especially tell when you write it in this way, this 2x cubed minus x squared plus 3x minus 4. This is definitely a function. So that weird thing, that weird definite integral with an x as its upper limit of integration represents a function, specifically a function of x. So part C says determine the derivative of that weird integral function. So determine the derivative of the definite integral from 1 to x of 6t squared minus 2t plus 3 with respect to t. And so using part B, we can rewrite that weird definite integral function. So we want to take the derivative of 2x cubed minus x squared plus 3x minus 4. And when we do that, we get 6x squared minus 2x plus 3. Stare at that for a moment. So, when we differentiate this weird integral function, what we end up with is the integrand with x plugged in. And so in other words, when you take the derivative of this integral function essentially the derivative and the integral cancel each other out. And a good question to ask is, does it always work out this way? And the answer is essentially yes. And the formal statement of, yeah, it works out this way, is FTC Part 1. But for now, let's go ahead and experiment with this a little bit. So if g of x is the definite integral from 1 to x of 6t squared minus 2t plus 3 dt, determine g of 2 and g prime of 2. Well, we already worked out that this weird integral function is actually equal to 2x cubed minus x squared plus 3x minus 4 from part B. And so if we want to do g of 2, well, we could use the integral function, definite integral from 1 to 2, 6t squared minus 2t plus 3 dt. Or we could use what we got in part B and do 2 times 2 cubed minus 2 squared plus 3 times 2 minus 4. And so it's much easier to use what we got in part B because we don't have to do any more integrating because we already did it in part B. So that's g of 2. And then the problem says to determine g prime of 2. Well, g prime of x is the derivative of that weird integral function. So 6t squared minus 2t plus 3 is being integrated from 1 to x. And we already worked out the derivative of the integral function, and we got 6x squared minus 2x plus 3 from part B. Part C. It's up high enough I can't see the letter that goes with it. That was actually part C. And so g prime of 2, we can go ahead and plug into that g prime that we worked out in part C. So 6 times 2 squared minus 2 times 2, and then plus 3.